Hello and welcome to the Cryosphere Pavilion. I'm Gabrielle Kleber, a researcher at the University of Tromsø in Norway. I'm here tonight to introduce our speaker for the event called Tipping Points of Arctic Climate. Dr. Heidi Silvestre will be monitoring the event tonight. She is a glaciologist and the Secretariat of the Arctic Monitoring Assessment Program, or AMAP. So take it over, Heidi.
Thank you so much. All right. Hi, everyone. Good evening. So welcome to our event on tipping points of Arctic climate. Thank you to ICCI. Thank you to the team from the Cryosphere Pavilion for hosting us. We have a great event in store for you guys tonight. I can promise you that. So as you know, in the Arctic, it is estimated that tipping points are likely to be passed if global warming exceeds 1.5 degrees. Changes in the Arctic are affecting millions of people within the Arctic, but also way beyond. So today we will learn about how quickly the Arctic is changing and why we should all care about what's happening in that beautiful region. So we have a great list of speakers for you today. We'll begin with keynote presentations, and then we will follow that with a Q&A session. So without further ado, our first speaker, Rolf Rudvan, you are the Executive Secretariat of the Arctic Monitoring and Assessment Program. And Rolf, the floor is all yours. Thank you. You have a little clicker here.
Okay. Thank you so much, and thank you all for coming. And again, thanks to ICCI for hosting us. So can you bring up the first slide? Good. What I'm going to say, I'm going to start by introducing the work. The work is background for the work is done by the Arctic Monitoring Assessment Program. Say a bit more about that. You can find a summary of some of the climate work. We still have some summaries. They look like this, and those that are left are on the chair. And so it's the first one in. So I'll start by saying a bit about the Arctic Monitoring Assessment Program. Then I'm going to say a bit about the climate change we are seeing, and I'm going to introduce the tipping points parts. So the Arctic Monitoring Assessment Program, or AMAP, as I'm going to say, not to twist my tongue, was established in 1991 and was a direct consequence, actually, of the speech that Gorbachev gave in 1987, opening the Soviet Union towards the West. So to find the first common denominator to cooperate on environmental issues was quite an easy and not so sensitive topic to start with. So AMAP was established as a part of what was called the Arctic Environmental Protection Strategy in 1991. Later in 1996, when the Arctic Council was established, we were organized as a working group to the Arctic Council. Just as the Arctic Council, we do have delegates from all the 8 Arctic states, the 6 what we call permanent participants, or what you know as indigenous peoples groups or organizations. We call them permanent because they have a permanent place at the table. And observers. Observers can be observing states or observing NGOs, so like WWF, World Meteorological Organizations, and so on. And what I should mention from the very beginning, we do rely our work heavily on a pool of about more than 800 experts distributed worldwide. So even though AMAP itself is a very small organization, we have a huge network of experts working for us. And we have some of them hopefully sitting in the audience today. And the Secretariat is located in Tromsø, Norway. So what do we do? Well, AMAP's mandate is to monitor and assess contaminants and climate change, the levels and trends in all parts of all compartments of the Arctic environment. We are investigating how it affects ecosystems, including socio-ecological systems, that includes the humans living in the Arctic, and also how climate and contaminants interact and in a multi-stressor regime on both ecosystems and humans. So what we produce are our assessment reports, and those are the backgrounds for the summaries you see there. That's our main product. The assessment reports are a scientific assessment report with a peer review, usually around 200 pages. We have one we call the BRIC, which is about 1,000. And we do know that to have a policymaker reading 800 or not just even 200 pages of science is rather hard. So we kind of condense them down, like 200 pages, we condense down to 20 pages of a scientific summary. And then, and the scientific summary, opposite of what you see from IPCC, the scientific summary is never negotiated. So it's a pure scientific summary. In addition to that, for the summary policymakers, we add in policy recommendations. And those are recommendations that have been negotiated among the 8 Arctic states, also in consultation with permanent participants or the indigenous peoples. We also do run a huge monitoring an assessment program where we do harmonize the way we measure things throughout the Arctic. That was in particular important in the beginning, particularly when it comes to human health, because you can't export samples abroad. And our work works as advice to the Arctic Council, but more importantly for us, we feed it directly into international organizations like the UN environmental organizations like Stockholm Convention, Minamata Convention on Mercury, the Air Convention, and we just had attended the ministerial yesterday on the climate and clean air convention. We attended the ministerial yesterday, WHO and others. And what you can see on the lower part here are the assessments report we produced for 2021, but also including a report we co-produced with UN some years back. So does this actually make a difference? And that's the question we try to ask ourselves every day, because we're not a scientific organization. We work in science to policy interface. So are we actually able to push the policy? Well, first and foremost, I would say that first success was the establishment of a harmonized monitoring program throughout the Arctic, and is still referred to on the way to do quality control and quality assurance today. When it comes to pollutants, important pollutants like what we call persistent organic pollutants, or PCBs, DDTs, and so on, and mercury, report the paper on the right-hand side and similar papers clearly states that those regulatory conventions were based upon Arctic data fed to UN through AMAP. Yeah. And also, I should say here, we also feed our data on Arctic warming into IPCC and UNFCCC. So, for the last, what is the state of the Arctic? And several of you have seen this before, but our latest report reports that the Arctic warms 3 times as fast as the global average. There are other reports saying 4 times as fast using a bit different data set. And we have seen that the temperature has since 1971 increased by 3.1 degrees. However, that's just part of the truth, because if you look into this area between Svalbard and Nova Zembla, we're already at an increase of 6 to 8 degrees. That puts the 1.5 target into perspective. It's not only getting warmer, but it's getting wetter. So we have, since 1971, precipitation have increased by 9%. However, it's not as it used to be. When it comes to rain, it's 24% more rain, but it's 21% less snow. So the winters are getting wetter, and that causes issues for the ecosystems. Also, permafrost is thawing. We've seen an average increase of 2 to 3 degrees Celsius in the permafrost since 1971 to today. And when it comes to the sea ice, it has almost halved since 1978. We've lost a bit more than 3 million square kilometers of sea ice. That equals the area of India. That is lost since 1978. And there's a massive loss of the Greenland land ice, which I guess Jason will come back to. We lost about 5,000 gigatons of ice since about the year 2000. So the Arctic is warming rapidly. And it happens so fast of what we call the Arctic amplification. The more it warms up, the less the albedo will be, the more humidity it will be, and it just keeps on accelerating. And that's the really scary part. However, even though these processes are accelerating, we still call them kind of linear. But what is maybe more scary is what we call, what I like to call the Arctic complexities of tipping points. And not to get entangled in the scientific definition of tipping points, in this session, what we call tipping points are processes where you have some kind of stepwise impact, and it's irreversible on the relevant time scale. So it may not be irreversible in total, but at least on time scale relevant for mitigation. As can you see on the map on the left-hand side here, and also on the figure on the right-hand side, those that are text line in yellow, all of them are taking place in the Arctic. So the Arctic is a hotspot for tipping points, literally speaking. And what's also quite interesting to see is that for a lot of those tipping points, they already start within the 1.5 to 2.0 scenario. And that's there. This is where I'm going to leave it to the next speakers, because they're going to go much more in detail on this. And so thank you so much.
Thank you so much, Rolf. That was such a great introduction to the event and also to the notion of tipping points. So you understood that what we're talking about here is really irreversible changes on human timescales. And it is clear that the Arctic is the best place to talk about tipping points, as you said, Rolf, it is a hotspot for tipping points. So our next speaker is Jason Box, that many of you already know. He's a professor at the Geological Survey of Denmark, GEOS, and he's a visiting scholar at the Bird Polar Research Center. So Jason will tell us about climate change indicators. And it's a recorded presentation. So Jason, if you can hear us.
Thanks for tuning in, and thanks to the International Climate and Cryosphere Initiative for hosting this session at COP28 in the UAE. I'm Jason Box, a climatologist and glaciologist at the Geological Survey of Denmark and Greenland, leading the Arctic Climate Change Indicators chapter of the Arctic Monitoring and Assessment Program's forthcoming report on Arctic climate issues of concern. This chapter includes contributions from 14 international experts across Arctic climatology. The Arctic climate system, as a cold pole of the Earth's planetary heat engine, has undergone profound physical changes since the mid-1980s. In the Arctic, it's only after the 1980s that the anthropogenic warming signal becomes obvious, punching through the noise. I'll now briefly summarize changes in more than 10 observational indicators of Arctic climate, most spanning the 44-year period 1979 to 2022 that covers the transition to a rapidly warming new Arctic. Owing to amplifying feedbacks and an increase in winter warm episodes, the Arctic surface warming rate in the recent 2 decades has exceeded 4 times that of the global average. Over the area where sea ice loss is greatest, the temperature increase is more than 7 times global. Around Greenland, the temperature increase since 1979 is twice global. The observational data exhibit widespread and statistically significant warming trends in air temperature and permafrost temperatures. We find increasing rainfall at the expense of snowfall, given how the melting point threshold is being crossed more often as climate warms, and how more moisture and heat are being pumped into the Arctic atmosphere from more north-south heat exchanges. The warmer atmosphere can hold and discharge more moisture in extreme rain and snowfall events we now witness more often than in the past. Satellite imaging has recorded a greening of Arctic tundra, driven by increased air temperature and precipitation, and field studies find increases in Arctic shrub heights from improved growing conditions of woody stem plants, along with a shorter snow cover season. Increased rates of Arctic coastline erosion are driven by permafrost degradation and more wave action that results from declining sea ice area and thickness. Glacier ice volume continues declining across the Arctic, led by a reduction in Greenland ice and followed in Arctic ice loss rate by Alaska and Arctic Canada. Notice, for example, how the rate of ice losses from the Russian high Arctic or Svalbard are increasing with time. This pattern of accelerating ice loss is consistent among all Arctic regions, as the glacier response is relatively slow because of their massive cold content that clearly shows signs of catching up with warming air and sea temperatures. Greenland remains Earth's largest regional contributor to global sea level rise, producing an even larger sea rise than from the much larger ice sheet in Antarctica. We find that increased wildfire area that is not only a major ecosystem disruptor and source of black carbon soot, but carbon emissions from fire combined with carbon emissions from permafrost degradation together are amplifying global warming. The more global warming, the more Arctic carbon release, and then some more global warming in a feedback process. Increasing fire and permafrost carbon emissions are not well captured by climate models that policy relies on as planning tools for the future. The weakness of modeling is not from lack of diligence on the part of science. It's for reasons like the model resolution tends to be too coarse to resolve the wavy jet stream and stuck jet stream patterns that produce extremes. Furthermore, the global carbon cycle is not well accounted for yet in climate models. And it's not the model's fault that not all known amplifying or damping factors are yet accounted. The issue is that in a lot of cases, we lack the physics and mathematical expressions to mimic how sensitive nature really is. Consequently, climate and Earth system models offer a mere facsimile of the infinite fidelity of nature. The models lack the sensitivity and detail we see when we venture to the Arctic. With model future ice loss being reported faster each time the models are upgraded, the implication is that society likely needs to prepare for more sea level rise. Modeling the future is hard, and when we compare how well modeling captures past ice and carbon changes, we get the clear impression that future warming and ice loss can come faster than forecast. The Arctic is responding to human effects on the climate system more rapidly than practically any other region on Earth, and the changes in the far north are being felt beyond the Arctic. Mounting evidence is linking rapid Arctic warming to mid-latitude weather extremes. Why is that the strength of the jet stream depends on the Arctic being colder than the mid-latitudes. Given the Arctic is warming faster than the mid-latitudes means that the jet stream is slowing down, becoming more wavy south-north, and getting stuck in highly amplified wave patterns that can produce either extreme dry or wet conditions, extreme heat, or even extreme cold, depending on one's location relative to the wave pattern. The global climate disruption feeding into Arctic-driven changes of mid-latitude weather already threatens the food and water security for billions of people and countless other species. Details about the overview I've presented here, including chapters about extremes, changing Arctic hydrology, or Arctic ocean acidification, appear in the Arctic Monitoring and Assessment Program's 2024 report on Arctic climate issues of concern. Thanks for tuning in, and do visit amap.no for more information.
Thank you, Jason. That was a great presentation. I mean, it is very clear that the Arctic is becoming warmer, wetter, greener, and also a lot more chaotic than before. It's crazy that we need to prepare for the worst consequences of climate change in that region. And what was fascinating about what he said was that these models are not perfect, they have their own weaknesses, and that things could be a lot worse than the worst projections from these models. So the next presentation is just as terrifying as this one. It's from Marta Trodau, who is a researcher at the Norwegian Meteorological Institute. And Marta will tell us about what's happening to the Arctic Ocean. She will explain that we're starting to observe more and more extreme heat events within the ocean itself. So Marta, another pre-recorded presentation, off you go.
At the Norwegian Meteorological Institute. Today, I will be talking about Arctic ocean heat waves, which are one type of extreme condition occurring in the ocean, and the reason why we care about understanding them are their potential for major impacts on ocean ecosystems. The Arctic Ocean is a very biologically diverse region. This summer, I was so lucky to get to experience some of this diversity. Shown here are some of the marine mammal encounters documented by the vessel I was on, except this mammal in the lower left picture. That's me next to a glacier on Svalbard. For all these animals, a marine heatwave event could have major impacts, leading to, for instance, a shift in their distribution or impacting their production cycles and food resources. But before we talk more about their impacts, firstly, what is a marine heat wave? At its simplest, a marine heat wave is a period of extreme ocean temperatures, just like heat waves on land are periods of extreme air temperature. However, they differ because marine heat waves can extend over larger areas and last longer. They represent, however, shorter-term change in ocean temperatures on top of the general longer-term warming trend of ocean temperatures worldwide. The number, intensity, and duration of marine heat waves are increasing globally. This figure shows the number of days with marine heat wave conditions averaged globally in different historical records from 1900 to 2020. And we can clearly see the increase the latest decades. Globally, this number has doubled since 1982. The most studied events that have occurred globally have revealed that marine heat waves can be devastating to marine life, as they've all been linked with disruptive changes in marine ecosystems. Some of the ecosystem impacts are shown on this sketch. The most well-known impact is perhaps coral bleaching, but they also include mortalities, harmful algal blooms, diebacks of kelp forests, and shifts in species distribution. When a marine heat wave strikes, it can force organisms to flee in search of cooler, more comfortable waters. Conditions can get particularly devastating for organisms that are immobile. Mass mortality and disease events linked to marine heat waves have been reported in wild and farmed fish populations. In addition, shifts in species distribution can lead to altered fishing practices and economic losses. The vulnerability of marine ecosystems depend on both the duration and how rapid the conditions develop, but also how extreme the temperature gets. The temperatures are considered extreme if they exceed a threshold above normal temperatures for that region and season. The question is, what is normal ocean temperature? Here we see the observed sea surface temperatures averaged between 1991 and 2020. This gives us a view of what normal conditions look like. At a specific day of the year, we can then consider how temperatures are compared to these conditions. The temperature anomaly for a day in August this year looked like this, where red colors denote warmer than average temperatures. Here we see large areas of red within the Arctic. However, to know whether the areas constitute marine heat waves, we need to look at the definition. Marine heat waves are characterized by how long they last, their intensity, and how often they occur, their frequency. The time series of sea surface temperature at one point in the ocean could look something like this, with time in days on the horizontal axis. Temperatures may vary from colder than average below the blue line and warmer than average above the blue line. When the temperature hits the threshold, the yellow line, and stays there for more than 5 days, we have a marine heat wave event. Marine heat waves can further be divided into categories depending on their severity. 5 categories have been defined, spanning from moderate to beyond extreme. The marine heatwave category is shown here for this day in August. The black regions are masked out due to sea ice. We can see that the red regions in the former slides met the marine heatwave criteria this day and categorized to severe to extreme heat waves in some areas, where the category reaches 3 and 4. But what can cause such a change in ocean temperatures? A range of mechanisms can lead to anonymously warm waters. We can consider some of the dominant processes in the upper layer of the ocean, the mixed layer, where water temperatures are relatively homogeneous. The mixed layer is warmed by sunshine and cooled by radiation emitted from the ocean surface and by heat loss due to evaporation. If the surface air temperature is warmer than the ocean below, the mixed layer may warm. Heating of the layer can occur with, for instance, a decrease in cloud cover that would otherwise reflect some of the sunlight away, leading to more solar radiation reaching the ocean. And in warmer wind conditions, there will be less evaporative cooling from the ocean and more heat remains in the layer. These conditions are typical when there's a persistent high pressure system over a region, also called a blocking high. Furthermore, weaker winds can result in suppressed mixing and a shallower mixed layer. With a shallow mixed layer, there's less water to heat up, which can generate a larger temperature response for given heat inputs. Ocean currents can also horizontally transport warm waters into a region. In addition, vertical entrainment or transport of water can impact the temperature. In the Arctic, the processes driving the surface temperatures are also influenced by sea ice. Solar warming is greatest in ice-free regions. While sea ice is mostly white and reflects the sunrise, ocean water is dark and absorbs the sun's energy faster. The distribution of thick ice that have been building for multiple years and thin first-year ice also plays a role. The thinner first-year ice can contain many leads or cracks. Heat fluxes from the air can pass through the ice and heat the water. Thinner ice drifts more easily, and this can also lead to sea ice removal and open up regions for heat input. Marine heat waves have been taking place in the Arctic, and studies show that their frequency, intensity, and duration have risen remarkably the past decades. Overall, the timing of being in the middle of a marine heat wave in the Arctic Ocean is early August to mid-September. Here you can see a map of a measure of the intensity of heat waves detected in the Arctic Ocean between 1988 and 2017. Red colors indicate more accumulated heat in the surface layers. The black line marks the average extents of this multi-year thicker ice cover, where we see the values remain relatively low within this line. The green line marks the average edge of the first year thinner ice. The increase in intensity was found to be greatest in this area. In the last decade, however, the areas with severe heatwave events have gradually extended northward, reaching the more central area of the Arctic Ocean. This figure shows how intensity evolves over the same period, with time on the horizontal axis and degrees north on the vertical axis. We can clearly see the increase in the latest years and how this impact is extending northwards. The increase of marine heat waves is found to be correlated with a decrease in sea ice concentration. To the right, we see the evolution of sea ice in 2007, and to the left, the time series of sea surface temperature from the area marked by the arrow, where these red colors denote temperatures above threshold and reveal that there were marine heatwave conditions lasting from July to mid-October that year. The most extreme marine heatwaves in the Arctic have each been accompanied by a record decline in Arctic sea ice, in particular in this year, 2007, but also in 2012, 2016, and 2020. The reduced ice concentration leads to less reflected solar radiation and more absorption in the ocean that further warms the sea surface temperatures. Upward trends in marine heatwave characteristics have been specifically remarkable in the Barents Sea, known as a climate hotspot. In the northern Barents Sea, increasing air temperature rates are up to 5 to 7 times the global warming rates. Also, increases in ocean temperatures have been approximately twice the global average. Strong positive correlations have been observed between sea surface temperature, surface air temperature, and marine heatwave characteristics in the Barents Sea. In 2004, a climate shift with amplified ocean surface warming occurred. The annual mean marine heatwave frequency tripled after 2004 until 2020, compared to the period 1982 to 2003. More than half of all days with marine heatwave conditions occurred in the last decade. And from this year, 2016 stands out. This was the year with the most intense event during 1982 to 2020, and also the year with the highest annual frequency of marine heatwaves. 7 marine heatwaves occurred, lasting for a total of 200 days. Here you can see the marine heatwave category within this red box from June through September 2016, showing consistently high values. The cause for this prolonged event was likely a persistent high-pressure system and southerly winds bringing in warm air. This impacted fish aggregations that shifted north and eastwards, and polar cod nearly disappearing in the southeastern central region. The Barents Sea has one of the world's largest concentrations of seabirds, account for approximately 40% of the Arctic primary production, and has some of the world's largest stocks of cod, capelin, and haddock. Most studies on the biological effects of marine heatwaves have been done in temperate regions, but we may anticipate that several of the implications carry over to the Arctic, and that could have pervasive impacts on the Arctic marine ecosystems and seabird populations. A great concern is then how the marine heatwave characteristics will evolve in the Arctic marginal seas and Arctic basin in future climate scenarios. This depends on the future changes in Arctic Ocean temperatures, which is linked to the evolution of 2 opposing contributions: a greater heat loss to the atmosphere due to a lower sea ice concentration and a weaker ocean layering, and ocean heat transport into the Arctic Ocean. A model comparison study finds a net warming of the Arctic Ocean under future warming scenarios. The warming rate in degrees Celsius per decade until the year 2100 is shown in this left figure, and it is found to be higher than the future warming rate for the global ocean, shown to the right. This so-called Arctic Ocean amplification makes conditions likely favorable for a further upward trend in marine heatwave occurrences. Indeed, a study specifically focusing on marine heatwaves in future scenarios found that they are projected to further increase in all their characteristics. They find that the largest increase in frequency will occur in the tropical Pacific and in the Arctic Ocean, as we can see by the dark red colors here in the map showing the probability of marine heat waves occurring at a 3.5 degree warming scenario. This table shows the increases in probability for marine heat wave occurrences in the Arctic Ocean specifically. We can see a large increase in the probability for the 2 degree warming scenario And in the 3.5 degree warming scenario, marine heat waves are found to be staggering 30 to 70 times more likely. Monitoring and predicting marine heat wave occurrences and impacts will likely get increasingly important. As mentioned in the beginning, we need to know the normal conditions to identify and characterize marine heat waves. This requires at least 30-year-long climatology with daily data. Most studies have been based on observed sea surface temperatures due to the sparse coverage of observations in the subsurface layers. However, marine heat waves can also exhibit considerable depth penetration, and about 1/3 exist at a depth with no surface expression at all, which are important for some ecosystems that are more sensitive to subsurface temperature anomalies. In addition to observations, we can use reanalysis simulations, models that incorporate available observations and provide a full depth view of the ocean. At the Norwegian Meteorological Institute, we have such models covering different areas of the Arctic. One example, the topaz model, is shown here in the highlighted colors of sea surface temperature. We are actively working on ways to use our modeling capacities to monitor marine heat waves in the subarctic and Arctic region. We hope we also can gain some insights into subsurface conditions through this work. With this, I want to thank you for your attention.
Whoop! Quite a sobering talk from Marta, but it's quite staggering to see, as the Arctic Ocean is getting warmer, how more frequent and more intense these marine heat waves will get. So unfortunately, this is not the only stressor that will affect the inhabitants of the Arctic Ocean. Temperature is one thing, but the next two talks are also going to be focusing on the Arctic Ocean. And the next one is especially focusing on the fish in the Bering Sea and on extreme events affecting the fish populations. So we have one last recorded talk before we have a talk in person. So the next speaker is actually Jim Overland, who is a research oceanographer at NOAA and at the Pacific Marine Environmental Laboratory. Off you go, Jim.
So the Arctic is seeing a large number of extreme events that are well beyond the previous record. And a real major one that I've looked at is the lack of sea ice in the Bering Sea, and this lack of sea ice has propagated to a major change in the ecosystem and influence on coastal villages. The Bering Sea lies between Alaska and Siberia, and the ocean is divided into two ecological zones. The southern Bering Sea is well mixed and has an oceanic ecosystem, where the northern Bering Sea, the ecosystem is based on tide to the bottom. And what's happened with less ice is the southern ecosystem with large fish predators is moving north. So the graph on the right shows how far south the Bering Sea ice extent has moved in every year since 1979, and notice the two minimum sea ice years in 2018 and 19. And once that got started, there was loss of ice, warmer sea and air temperatures, and this was partly driven by southerly winds and a wavy jet stream. So this really affected the ecosystem. The large predator fish, which were pollock and Pacific cod, moved north. In 2019, there were like 20 times the amount of pollock and cod in the northern Bering Sea compared to a baseline year of 2010. In 2020, there were less pollock and cod, but still a major increase over the baseline. And these large predatory fish eat everything smaller. So it was a major reorganization and loss of the smaller forage fish in the middle part of the food chain. And warmer temperatures changed the base of the food chain. So this had all sorts of compounding impacts, the loss of small crabs and northern salmon runs, and there was mortality for seals and seabirds, and so this affected the food security and economics of all the coastal communities. So shown there are subsistence eggs collection and butchering of a walrus. So the tie of the loss of sea ice was related to the weakening of the Arctic front. That these are sea level pressure maps for different years, and the top one was during the 2018 and 19 period where the Beaufort High was very weak, and that allowed storms and southerly winds and to keep sea ice in reduction. But the minimum ice doesn't occur on every year. In the last couple of years, we've gone back to more normal sea ice. So these minimum sea ice do not occur in every year. And so there have been catastrophic changes to the ecosystem and coastal communities around Bering Strait. And while sea ice minimums will not occur in every year, we are predicting that in the future, we won't have real major large sea ice advances, and we'll have minimum sea ice in probably 2 or 3 years per decade in the next couple decades. So that's my overall pitch, that there are major new extremes. There are new indicators of climate change in the Arctic.
Thank you so much, Jim. Wow, these numbers on fish populations are absolutely crazy. But it was nice to get a reminder that behind these changes, we have lives and livelihoods. So let's never forget about the cultural and societal impacts of all of these changes that are occurring within the Arctic Ocean and the Arctic itself. So there's one last stressor, I guess we haven't talked about yet, at least not too much, which is ocean acidification. And we're so glad to have a speaker in person, one of the world's best experts, Professor Helen Finlay, who is working at the Plymouth Marine Lab in the UK. Thank you for being here, Helen, and the floor is yours. Thank you.
Thank you for letting me be here to talk to you about my pet subject, oceanification. So let's see, that's the wrong way. Yep. That's also the wrong way. You have go next, keep going. Next. Ah, there you go. I've gone too far. Well, there we go. It's the end of the day. So ocean acidification, we've heard a bit about Barents Sea, and this is actually the ocean acidification stripes. So we have climate stripes, I think everyone's aware of. We have worked on a project with ETH Zurich, and they decided to use their satellite modeling data to produce ocean acidification stripes. So I thought it was relevant. You can go and see the website, take a look at that. You can see how the pH has changed. 23% increase in acidity in the Barents Sea over the last, well, since 1982. So 40 years. It's making me think about how old I am. But yeah, so I'm going to explain a little bit about oceanification and relation to tipping point. So just to make sure we're all on the same page, what is oceanification? The oceans naturally take up carbon dioxide into the water. This is a really great thing. They take about 25% of the CO2 emissions that were put into the atmosphere. And if we didn't have that sink, we would be seeing even more global warming than we already experience. But what happens is it goes into the ocean carbonate system and it reacts, and that's a natural process, but we're adding too much too quickly. And that's resulting in a shift in this marine carbonate system, resulting in a decrease in pH or an increase in acidity and a change in what we call the carbonate ion concentration. And that's really important when we think about organisms that have calcium carbonate shells, so things like corals, shellfish, mollusks, or your seafood will become, essentially the water becomes a corrosive after a certain level of conditions in there. So we know that the atmospheric CO2 levels are increasing. That's the black line in this graph. We have good data on that. This is from the Mauna Loa CO2 observations. We know that the ocean CO2 is also increasing. We've now got good global data for that as well. And we can see directly related to that is the decrease in the ocean pH. So here you can see the decline in pH, that's getting more acidic. And this is the ocean carbonate ion concentration that we were talking about. So again, we've got this data. We know the chemistry is changing. We can see this around the world. So the oceans are becoming more acidic and more corrosive to calcium carbonate minerals. The Arctic Ocean is, again, like we've heard across all of these factors, the place where this is happening most rapidly. And this is the future projections, well, up to present day and future predictions for the Arctic Ocean, this level of corrosivity, if you like, the saturation state. So as you go down, you get to this level 1. Chemically, that's where the ocean becomes corrosive to these calcium carbonate minerals. And as you can see, for the Arctic Ocean, it is just the low emission scenario that will stop us just about, in some places, from reaching that level of corrosivity in the surface oceans. On the right side of the panel here, you can actually see how that changes with depth through the water column. So not just the surface water that we're concerned about, actually this corrosivity is actually worse at depth. So you can see the black line there is where we are now, going through the water column from the surface down to the 2,000 meters. And as we move forward in time through low emission scenarios in blue to high emission scenarios in red, you can see that actually pretty much all of those scenarios will bring us at some point to corrosive conditions in the Arctic Ocean. Acidification requires geological timeframes to recover from, and I think this is important, especially when we're thinking about these tipping points, is will they get past a certain level, will they get past a threshold, will they be able to recover? Particularly for the Arctic Ocean, where there's less carbonate ion minerals in the system already, it means that they're not able to recover from these events. These processes take geological timescales. It's geological weathering of calcium carbonate rocks that actually buffers this system. And that's no different to the rate that we're adding the CO2 to today. We're not increasing the rate of that weathering. We're actually keeping that the same as it's always been. But so anything that we do to the system will result in essentially long-term recovery for these events. So if we stopped emitting carbon dioxide at these various levels by the end of the century, then these are the sort of trajectories we expect to see up to the year 2500. So you can see that we're locked in already to a certain amount of acidification. And this just kind of takes that point one step further. So this is really new data that we worked with the UK government to produce. So thinking about these hysteresis or these tipping points, can we use the atmospheric CO2 concentrations and the projections to look at where these levels of corrosivity are going to occur? This first panel on the left shows as we increase the atmospheric CO2 concentration, we actually see this decrease in corrosivity or increase in corrosivity, if you like. So the red line represents a high emission scenario. And then as you go through to the dark blue line is the low emission scenario. You can see that depending on how quickly we acidify the oceans, how quickly we add carbon dioxide to the system is how quickly we will reach these levels of corrosivity. But what's actually really important to recognize, again, just on our 2100 scenarios, if we stick to the 1.5 low emission scenario, you can see that this isn't a linear effect. So the panel on the right there shows that even as CO2 emissions come back down after the year 2070, through 2080, 2090 to 2100, so the CO2 levels are falling back towards 400, the level of corrosivity is still staying at that low level. So it's past this tipping point. We've gone beyond already some level of commitment to acidification in the Arctic. You may come across this planetary boundaries and talk about thresholds by Richardson et al. The most recent assessment came out in September, I think it was this year. And they put global ocean acidification just under the safe boundary of safe operating space, they call it. And again, this is kind of another way of thinking about tipping points. And what we're looking at the moment is whether we can really break this down again. So we talk about these averages, global averages of 1.5 or global averages of declining pH, but actually when we break it down to regional changes, ocean acidification has crossed that boundary, the same boundary that they talk about for the global average, by some margin in the Arctic Ocean and the Southern Ocean. And one of the things that Richardson et al. Wanted to do was to use the boundary of 80% of pre-industrial conditions to make sure that the polar oceans would not cross this level of undersaturation. And what the panels on the right there show are maps of the Arctic Ocean in terms of their saturation state. So red is essentially more corrosive, and then as you go white, that's good conditions. But even pre-industrial conditions had 0.5% of undersaturation in the Arctic Ocean surface waters. But what we've seen is that actually, even through to present day, the observations are showing us that we're exponentially increasing that amount of undersaturation in the surface waters. And so we're already experiencing undersaturation in the present day. And so we have crossed that safe operating boundary in the Arctic regions. But how can we link that to the biological effects? Why does it matter? Why do we care about the ocean acidification? Well, there's many reasons for caring about acidification, just like you and I, all marine organisms have to monitor and regulate their internal acid-base balance, their pH in their blood. But we're particularly concerned about calcium carbonate producing organisms. So this is a really good example of a shelled organism. It's a pteropod, it floats around, it's also known as a sea butterfly. On the top picture there is a healthy pteropod, and you can see it's got a kind of nice clear shell. It's maybe difficult to see from the audience there, but the bottom one is one that's been exposed to conditions which are corrosive to its shell. And you can maybe just see on the side here, these areas here, with like stripes, which don't come across in this one. There's cracks here, there's cracks on here. And generally it's in much poorer condition. It's experiencing dissolution, so it's dissolving away even while it's living. And what Nina Bednarczyk and others have shown is that actually these pteropods are not subjected to this chemical threshold of 1. They actually will be impacted at much higher levels, so anywhere up to about 1.5. So in the Arctic Ocean, they're already experiencing that. And what they can do, what Nina and others have done, is then produce maps to show where these aragonite conditions are happening in the Arctic. So that's the panels on the left here of the Arctic Ocean and Southern Ocean. Just for comparison, you can see in red again is beyond this biological threshold of 1.9. And then the percentage of pteropods we expect to find that have severe dissolution. So again, red is bad as you go through there, and you can see pretty much large portions of the populations are subjected to, we would expect to find at least 50% of pteropods to have severe dissolution. And there's growing evidence of damage in populations and oceanification hotspots. We've got evidence of calcification rates decreasing in the Southern Ocean. We've got evidence of larval crab exoskeleton dissolution, and that's affecting things like how they receive information, how they can detect information and respond to the environment. So I just wanted to kind of bring together a bit of the oceanification story with some of the warming, because we've heard a little bit about that today from others. And just a bit of a precautionary tale, I suppose, in that the IPCC report has these lovely figures. And this one is about fisheries yield. And if you were to just look at this without reading any of the data, right, I think most people would agree that green looks good here. So the Arctic's going to be awesome. Even at the kind of high-end scenarios, we can go away and have catch lots of fish. It's going to be brilliant up in the Arctic. But actually, that's not the case. And if you read the small print, it says projected changes in the Arctic regions have low confidence due to uncertainties associated with the modeling of multiple interacting drivers. And that means that the fisheries models that are included in these basically take into account some warming effects, but they take very little account of sea ice loss, things like acidification, multiple stresses in other ways, the freshening of the Arctic Ocean, the changes in the salinity budget. So I want to just bring acidification into the equation, and this goes back to the AMAP Arctic Ocean report that was produced back in 2018, who were able to provide some case study examples of impacts on certain fisheries species across certain regions of the Arctic Ocean. So you can see these in the report. So there's a couple of examples there. There's Norwegian sea urchin and kelps. Again, oceanification and warming are suggested to reduce the potential of urchin harvest by a factor of 7. Norwegian Barents Sea cod, ocean acidification makes stock collapse more likely, especially in combination with warming. Greenland shrimp, there's insufficient data, but there's some evidence of impacts. Alaskan king crabs, there's a decrease in crab catch due to oceanification. And the Canadian Western Arctic bioregion, it's a really interesting case study, that one, where they think about the risks and dynamics of the socioeconomics as well, where there's also increased marine productivity due to warming and little effect by acidification. So you can see that actually we really need to be taking into account all these multiple drivers in our assessments of impacts to things like fisheries. So just as a kind of bringing that together for the Barents Sea cod, I just wanted to highlight this one. These profiles basically show what you can achieve in terms of maximum catch against temperature. So temperature goes across the axis. If you have a warming only scenario, basically white and yellow is good, purple is bad. So you would expect that there's more mortality in the system if you have higher rates of warming sort of outside of the thermal range. If you add acidification into the equation, basically what you can see there is that purple drops down. So the risk of stock collapse massively increases once you have that multiple stressor in there. So you can see basically the takeaway from this is that the purple is bad. That's high stock collapse, and from going from a warming only scenario to a warming acidification scenario, you really bring that stock collapse down. So the take home from that is that future warming and acidification at these levels puts that large fishery at risk of collapse. And if they want to continue to fish sustainably, then they have to actually reduce fishing activities to be able to sustain that profitability. And again, this is new data. This is a PhD student of mine who finished this spring. He's been using satellite data to try and make better measurements, but more measurements of carbonate concentration changes or ocean acidification changes across the Arctic Ocean. And she was looking at whether we can map that against kind of the life histories of species in the Arctic. And this is just a really nice example of where you can see the pod life history on the left here, where you can see in dark blue is the spawning areas. You've got the sort of lighter blue are where the juvenile and adult feed. And you can see that what we know from acidification experiments in the lab is that actually these juvenile areas, the egg spawning areas, it's those life stages that are going to be most impacted by acidification. And actually, if you map that onto where we're seeing the highest rates of acidification in the region, then that's the fastest rates of change are in these areas where early life stages are distributed. And so again, that's another reason that we need to be taking into account these multiple stresses. So you hear a lot of people talk about how fisheries are going to be moving northwards and these life stages are going to be distributed differently. But we do need to take into account the fact that all these other stresses are going on alongside that. And they may not be able to move northwards. They may be trapped by these other stresses that have the potential to impact them further into the Arctic Ocean. So I'm going to kind of end with just saying that acting now prevents the worst. I like this figure because it really highlights the difference between urgent action and sticking to low emissions versus carrying on the way we're going and having high emissions. So this is from the IPCC Special Report on the Oceans and Cryosphere Climate. I never get that right way around. SWOC report. So by the year 2100, if we stick to low emissions, you can see the areas of red represent where the waters become essentially corrosive to these calcium carbonate minerals. Quite limited in the low emission scenarios. It's pretty good outcome, I would say. High emission scenarios, not so good. Pretty vast areas of both the Southern Ocean and Arctic Ocean will become undersaturated year round. So the option now is what we do. Where do we go from here? And we still have this choice that we can make. Do we stick with this low one where we have very low impacts to the or ecosystem? We're still locked into a certain amount of that, as I hope you've got from this talk and the other tipping point talks, is that these things are happening. They're happening rapidly, but we still have a choice as to how far we send these things, whether we do cross those tipping points and whether we move on, or whether we can kind of stabilize the system a bit and not go so far. So yeah, just in conclusion, polar oceans are far more sensitive to rising temperature and CO2 than the global average, and I think that's really important. You've heard about the Arctic warming being 3 times as fast as the global average. It's the same is true for acidification. Changes are very long term, but directly depend on the rate of CO2 emissions and the rate of uptake by the oceans. And significant damage can occur at 2 degrees. So 1.5 really is the one that will limit these vast ecosystem impacts on fisheries as well as many other impacts. And so acting now will prevent the worst. So I'll end there. Thank you.
Thank you. Thank you so much, Helen, for this very, very comprehensive and extremely scary talk. I think it was great that you reminded us of the fact that we can still avoid the worst consequences, even if we keep at or below 1.5 degrees. Important to always have some hope and think about solutions. Before we move on to our Q&A, I'd like to extend my thanks to my colleague Janet Polak, who's probably watching. Hi, Janet, and she's put together this great event. So thank you, Janet, and hello from Dubai from afar. So we have time for questions and answers with the 2 speakers that we have in person today. So do you have any questions, and do we have any comments online by any chance? If we don't have any questions, perhaps I'll start. I have a very simple one that you can absolutely expect. What would you say to the policymakers, to the climate negotiators who are, 300 meters away and have important decisions to make? If there was one sentence, to raise awareness about what you're working on at the moment, what would you tell them? Could you come here to answer? Thank you.
In one sentence, I think we have enough evidence to act. It would be my pitch really, is that you can always do more science, and as a scientist I'm like, yes, please give me more money, I'll do more science. but we have enough evidence, and I think we've demonstrated that just in this hour, that we need to be acting now, and what we do now has severe implications, not just for the next 100 years, but for long-term changes.
Would it be too late next year, you think?
I think the longer we leave it, the less easy it's going to be to stop a lot of these things that are already in momentum. So we need to be urgently acting. We needed to be acting 30 years ago, but we're at this point where we are now. And I think for me, it's important that we recognize we're in a place where we're really running out of time. And especially for the acidification issue, the only thing that will stop acidification is mitigation of CO2 emissions. It's directly linked. So you can come up with lots of other kind of solutions that are unknown. We can try them, but we don't know. We'd just be manipulating a system that we're already playing a big experiment with. So we really need to be reducing those CO2 emissions.
How?
May I ask? Oh, sorry.
Yeah, well, if I can just yeah. I was just going to ask, how many of you know Eunice Newton-Foote? She, in 1856, she was the first, a brilliant scientist. I don't think we have any picture of her, but she presented the first evidence of the heat capacity of carbon dioxide. It was done 1856 in an American conference. That is about 167 years ago. We spent the next 100 years neglecting the fact, more or less. Well, we had Svante Arrhenius hypothesizing how this increased CO2 would actually affect the global condition. Then we spent the next 50 years denying the fact, and now we spent the last 17 years trying to figure out how to deal with the fact. That's the important thing. We do have, as Helen says, we do have the evidence. We have the evidence for 167 years, but we have not acted. And that's the important thing. And I think even if you look into the Paris Agreement, if you just have implemented those commitments in Paris agreements, I think I might be wrong, but I think we then will be heading for a trajectory to 1.7 or something. So it's all about acting. We have the evidence to act. What we need, talking about evidence, is the evidence about. We need to know, to understand, what do we need to adapt to? What are the extreme consequences? How will the mitigation efforts, how will that actually affects also other things? How to adapt to mitigation efforts, and how to prepare ourselves for the future scenarios. I guess that's kind of the take-home messages to the policy.
Yeah, I'm just interested in the presentation, by the way. It's very frightening to me.
I mean, I know you, but the rest may not do, so please introduce yourself.
Greenland Ice Sheet from Receding Arctic. We are this NGO working on trying to find some ways to prevent these tipping points, tensions. And yeah, you said that there could be some. Have you heard of any idea how the acidification could be made even less worse? Of course, we should stop emissions.
Beyond emissions, yeah.
Has there already been?
Yeah, absolutely. So there's a lot of talk of carbon dioxide removal technologies. So the ocean versions of those, one of the prominent ones is something called ocean alkalinity enhancement, or enhanced weathering, which is where essentially we're speeding up that geological process of weathering. So you would be adding calcium carbonate into the system, which would then allow the ocean essentially to take up more carbon, but actually regionally it mitigates against ocean acidification. But it's one of few. And there's still a lot of unknown. So other kind of marine carbon dioxide removal things that people are talking about are things like growing kelp and seagrasses, and which is all good. We know that photosynthesis takes up the carbon dioxide, so locally again you get amelioration of acidification. What we don't know is the long-term impacts of that, or the kind of footprint of that. So locally it might help, but actually there's studies that are showing that even within a kelp forest you get very different pH levels or acidification levels going on depending on where you are, whether you're at the bottom, whether you're at the surface, where you are what other creatures are around. So there's a huge amount of unknowns in terms of what that actually means for both mitigating against acidification, but also the general kind of idea behind carbon dioxide removal. So
Could just add in, I think we maybe have under-communicated also like the importance of the Arctic oceans when it comes to CO2 uptake globally, because even though they, and you know the numbers correctly, but they take up more than, I think it's 3 to 5 times as more compared to its volume if you compare it to low latitude. So it's really an important mechanism for taking CO2 out of the atmosphere. But as you say, like when we kind of reach the buffer, end of the buffer, it will kind of stop taking off the CO2 at some or slow down the process. So it is kind of our rainforest in many ways. But you know the numbers much better than I do.
yeah, no, you're right. I don't know the split between the Southern Ocean and Arctic Ocean, but it's somewhere like 60% of the carbon dioxide is taken up by the polar oceans alone out of the global ocean. So they play a huge role in taking up carbon dioxide. The Arctic's an interesting one because it's basically a collection of fresh water coming in, and a lot of that fresh water doesn't have high calcium carbonate minerals, and so it tends to have a lower ability to buffer against changes in acidity. So it's a much more sort of freshwater system compared to some of the other oceans. So again, it kind of is that combination of the chemistry, what's the ocean already like, versus how much CO2 we put into it. You've got loss of ice that allows more CO2 essentially to go into the ocean because you remove that cap, if you like, which has been, so actually in some respects you get an enhanced carbon sink in the polar oceans as you remove the carbon dioxide, but actually they only have, like you're saying, a certain capacity they can take up, and at some point that capacity will slow down or stop. And we're not quite sure when that will be, but it has implications again for that climate feedback system.
Why does the carbon uptake go up when you remove the ice? Is it because of the temperature of the?
It's because like opening, if you have a soda bottle and you open the top of the bottle, you have more flux between the ends. So it's just the opposite way around. Because when you take away the sea ice, you will have more waves, and the waves bring the air into the sea, so including the CO2. So it's more like the mixing of gas and liquid. It's sorry, I think Mr. James, I think you should go with ladies first.
So thanks both for those of you online for really great talks. I especially like having your ocean acidification stripes. I think they're a great way of communicating to the general audience what's happening. Obviously, we've got the warning stripes, we have buildings behind you, and now biodiversity. So my question to you is, can you think of anything else we need stripes for? Perhaps a number of fossil fuel overs, for example.
That would be quite a challenging one, I think. Well, those stripes, first of all, those stripes are available. If you just Google ocean acidification stripes, you should come up with the website. It's been done in discussion with Ed Hawkins, who developed the climate warming stripes. And I was going to make a t-shirt with the warming and acidification ones together, but I didn't get quite that geeky. But actually, when I saw these stripes earlier, I actually thought it related to snow. So maybe there's ones we can do for snow, glacial loss. I mean, pretty much everything that has an indicator that you've got more than 20 years worth of data, I'd say you could put a stripe to. I think the longer the data set, the better, because it looks a little bit more dynamic. That's the great thing about the Ed Hawkins stuff. It's a long time series for many of those. There's many, I think.
I think if I would suggest some, if you're looking into like some of the more severe indicators here, like permafrost temperature, soil temperature, for instance, permafrost thaw, glacier melt, and maybe species displacement, and ultimately, if you're speaking outside of the Arctic, it will be like loss of suitable habitat for food growing for humans. It will be like a really important one at some point when we start losing those fertile areas, particularly in Asia, talking about Bangladesh, Pakistan, and those that will have problems with the increased sea level rise.
You could see it almost being done for all the sort of essential ocean variables or the WMO kind of indicators or something. So yeah, potentially.
The thing that Shannon Lee University, for those online, the thing that strikes me about this COP, as against the two previous ones that I've attended, is that there's much more prominence of climate interventions, and several of them are focused on the Arctic. So my question is for you, Rolf, about whether the Arctic Council or any of its working groups have any guidelines or recommendations or rules around this, in the same way that you've had guidelines for tourism, for example, in the past, or marine protected areas. If not, please can you?
I guess this is actually an excellent point to introduce the person just sitting behind you. So Mariana, if you could just say who you are, so first, so if you can just say who you are and what you do, and then I'll tell about that council afterwards.
Yeah, my name is Marianne. I'm a scientist. Background from politics, and I'm working with a group of scientists that are working on to see if the seabed current could slow down the melting of the ice sheets in Antarctica and also here in that part, the total part of warm water of the sea there. Just to buy us time, not to not produce emissions, which is the absolute undeniable, unquestionable goal number one for everybody, but to see if it's possible by municipal interventions to buy more time for people in Tonga and Bangladesh and elsewhere.
So just to continue on that, the climate intervention is not a topic under the Arctic Council at the moment, but it has been, as Marianne said, there was this report published by University of Arctic, or people working at the University of Arctic on different types of climate interventions. Whether it will be a topic under the Arctic Council is this. It doesn't follow naturally the mandate of AMAP to work with climate intervention. But what I do see as a potential is to look into consequences of climate intervention, both on the positive side when it comes to mitigation, but also on what kind of other effects can it have. And I mean, it's very much related to what we see today, like those changes that can happen very abruptly and which are very hard to predict in long term, because they're non-linearity, because they're partly irreversibility. And I mean, both Anton and Marianne knows a lot about this, and there's a great scale of what you're doing. And what's important, and now, please, this is my personal opinion. It's not a policy of the Arctic Council, but I allow myself to be a bit more free speaking now. And something I probably will discuss with Marianne later. It's like this also kind of implies some kind of governance system, because there's no governance system at the moment. So at the moment you can implement climate intervention locally, and it will affect globally depending on what kind of measure you do. And what is, I mean, put into the way we work in is that I mean, people living where I grew up, and I mean particularly those indigenous peoples living in the Arctic can be affected without having any kind of vote to what's happening. And that, to me, and again, this is my personal opinion, that is a very important question to raise, because I guess, like several of you and like Anton who said already, we do see increased concern raising when it comes to climate change and the need for doing some immediate measures, immediate mitigations, and to do that without a governance system, it is, I would say, that's a risky business, because you don't know the state that may face the most severe consequences of climate change may not be the state that are impacted by the side effect of the intervention. So that is something that's really important for me, in principle of the way we work together in our work.
I'm going to be a bad moderator here.
Now we brought all these joyful messages.
No, I think thank you so much for bringing up geoengineering and different interventions that we can do. This was actually And some of us were in the room in Paris just a few weeks ago. You know, we had the Polar Summit, the One Planet Polar Summit in Paris. And this was a very important topic of what happened in Paris. We were extremely lucky, actually, that one day to have Valérie Masson-Delmotte, which is one of the best climate scientists on the planet, talking very clearly about the consequences of geoengineering. At the moment, let's be very clear about geoengineering. It's not buying us more time. It's buying more time for the fossil fuel industry. This is really what is currently taking place. And I hope this is, I'm sure, not what you have in mind. But the problem is that at the moment, by building sea curtains, by trying to partly block sunlight, this is a way to avoid fixing the problem at the source. And we know that by far, the cheapest, the most efficient, and the safest way to save our climate today is to phase out fossil fuels. There are no other ways around it. I hope we find solutions for Bangladesh, for the Netherlands, for all of these places. But there is zero doubt that the best way is really to phase out fossil fuels. And we certainly have high expectations for COP28. But it's true that when we look at geoengineering at the moment, it's aiming to fix one thing, but the negative consequences will be absolutely major everywhere else. So I'm so glad you're working on this, because we really need bright people to focus on these issues. But we need to be fully aware that at the moment, we don't have a governance mechanism and the huge amount of funding that is going into geoengineering. Just a quick example, when we look at carbon capture and sequestration, if we want to implement this at the level we need it to be implemented today, it would require the consumption of electricity of the entire planet. So at the moment, it's not perfect, far from it. We will probably need some CCS in the future, but let's not give up on all these natural ecosystems that we have, which are by far, as you so clearly described, the best carbon sinks that we have on the planet. So let's explore, of course, these so-called options, but let's be extremely careful, because, we don't want to keep playing and poking our climate system. Can we take one last question, perhaps, from these bright people? Is it all good? Well, thank you so much.
Thank you.